Hello students, I am Dr.N.R. Sheela, Assistant Professor, Department of Physics. I am going to demonstrate laser experiment for you. So which has been split into three parts. One is determination of wavelength of laser beam. Next, particle size, followed by numerical aperture and acceptance angle. So first part will be wavelength of laser beam. For this experiment to be carried out, certain apparatus is required. One is, we are going to determine wavelength of the laser. So the foremost thing what we require is laser. Laser source, which is in our laboratory, what we are using is a diode laser. So regarding the types of laser, we have much discussion in our theory part. So the laser type what we are using here is diode laser, and that is one major apparatus we require for to demonstrate this particular experiment. Next is grating element. Next is grating element. What is grating element is actually, it is a plain glass plate in which number of lines have been drawn using a diamond needle. So once these lines have been drawn, it will act as a slit. The light will be, in this you have a transparent and opaque portions have been formed by drawing such lines in this plain glass plate. So thereafter it acts as a diffraction grating. So in this, if you observe 2500 LPI, it has been manufactured in this manner. So such grating is being used to demonstrate this particular experiment. What it means is 2500 lines per inch has been drawn using diamond needle. So this is the second apparatus which we require to demonstrate this experiment. And then we need a screen to get a diffracted images. So the screen what it has been used is, this is what is called as the screen cum scale. So this scale can be used as a screen which is calibrated so that we can measure the distance between the various orders directly. For that purpose, the scale has been used as a screen here. The calibrated scale is being used as a screen. So these are the major things which is being required to demonstrate this particular experiment. Though you are going to do this experiment in a laboratory lively, this video will be helpful for you to know much about how to do this experiment. So when you repeatedly do play and watch this video, you will have a much idea before coming to the lab or even after doing the laboratory experiments. Hope you all clear about the apparatus that is required to demonstrate this wavelength of laser beam. So this is a grating element. This has to be fixed onto the grating stand. After fixing the grating element onto the grating stand, you can switch on the laser source. So as I said earlier, the grating element in which number of lines have been drawn, that is about 2500 lines per inch have been drawn in this grating element. So in such a grating element, when the light is made to pass through, due to that lines drawn on that grating, various orders have been displayed on the screen. That you can see the various orders which is being displayed on the screen, which is due to diffraction. Based on the principle called diffraction, these lights have been, this laser light get diffracted and it is being viewed on the screen as various orders, which has central maximum and different orders on the left side of the central maximum and right side of the central maximum. So when the light is passing through this grating element, due to diffraction, you can see various orders displayed on the screen. That is what you are viewing now. So when you clearly observe the various orders which is being displayed on the screen, the central one is very bright and left side of this you have various orders. To its right side you can also see various orders. So that orders have been displayed due to diffraction. So earlier by passing through this grating element, I told you central maximum will be there and various orders to its left side and right side will be displayed on the screen. So that is what you can see here. The central maximum, which is very much brightest part in this image, you have to coincide exactly with that of the 0 of the scale. So by adjusting or by sliding the scale, you can make that adjustment promptly. So now your central maximum is exactly coincide with that of the 0. So when I move the distance between the grating element and the screen, you can observe there is a divergence when I move front and back, this grating element or grating stand. You can observe the convergence and divergence of the orders with respect to the central maximum. So it is coming very close to the central maximum, the orders on the left side and right side when I move front. When I move back, it has been diverged to that of the central maximum. Therefore, you have to measure the distance between the grating element with that of the screen. At what distance you can see the orders on the left side, at least 5 orders on the left side of the central maximum and 5 orders on the right side of the central maximum. As the distance have been increases, this intensity of the orders will become faint, it will become dull. Therefore, fix in a prompt distance such a way you have at least 5 orders on the left side and 5 orders on the right side. So now you can see the first order, second order, third order, fourth order and fifth order. Fifth order is very dull, but you can observe. So thereafter you can't see. So similarly on the right side. So using the scale itself, what is the distance of the first order from the central maximum? So this is left side first order. So you can see in the scale where it has been coincided. It has been coincided at 1 point. So each line is, there are between 1 and 2, you can see 10 lines have been drawn there. It has been calibrated in such a way. So each line is 0.1. So therefore it is 1.2. First order, left side is 1.2, right side is 1.1. So those distance has to be tabulated in the tabular column, which has been shown in the, which has been drawn in the manual. So the lab manual will be given to you. So in that, this particular experiment, aim, apparatus, formula, tabular column, all these things will be there. So after measuring, the data has to be tabulated in the tabular column. I'll show you now. As I told you earlier, the distance between the grating element and the stand and the screen has to be noted. I'll repeat, the distance between the grating element and the screen has to be noted. So this is a place where you fix the grating. Therefore, it has been noted as the distance is here 33.5 and to that of the screen it is 10. So 33.5 minus 10, which is 23.5. So the distance between the grating element and the screen has to be noted down as D is equal to 23.5 centimeter. That is, it is given on the tabular column, on the top of the tabular column as capital D, which is distance between the grating element and the screen. In our demo, it has been noted down as 23.5 centimeter. Later, we'll convert that into meter. Now move on to the distance from the central maximum to the various orders. So from the central maximum to the left side first order, it has been noted down as 1.6 centimeter. Directly you can note down from this screen come scale itself. So that particular first order, that is first part, what I mean is first order here. You should not call as part, it is to be called as order. The first order has been coincided as 1.6 centimeter in this screen. So that has to be noted down in the tabular column. Left side first order, order 1, left side reading 1.6 centimeter. Similarly, when I move on to the right side first order, it is also coincide in the same manner 1.6 centimeter. Sometimes exactly left side and right side will coincide. Sometimes 1 or 2 0.1, 0.2 divisions there will be a mismatch. Left side may be 1.6, right side may be 1.5 or 1.7 like that. But in this case, this both are same. So right side 1.6 centimeter. So left side first order, right side first order, which has been noted directly from the screen. So when second order, second spot, that is second order, third order, fourth order, fifth order. So where the second order is being coincide on the screen, you have to note it down for the left side and similarly for the right side. And for third order, where third order left side, where it is coincide on the screen, note down that reading. Similarly for the right side. And when you come for the fourth order, where the fourth order is coincide on the screen for the left side as well as on the right side. So in that way you can note down the readings which has been tabulated in this tabular column. I have noted down the distance from the central maximum to the left orders, various orders, and to that of the right orders. For first order left side, second order left side, right side, and third order left side, right side, fourth order left side, right side, and fifth order left side, right side. I have noted down and tabulated here. So the complete tabular column you are viewing now. So for first order left side, right side, mean value is noted down as x. How to take the mean, you hope you all know. Anyhow, I will repeat. Left order 1.6, right order 1.6, add and divide by 2, you will be getting what is mean x. Similarly 3.2 and 3.2, here 3.2 itself the mean, and for third order the mean is 4.8, and here you have left side 6.4 and right side 6.2. When you add and divide by 2, you will be arriving 6.3, and 8.4 left side and 8.0 right side. The mean value is 8.2. So here you can see the what I said earlier. Sometimes the left side first order and right side orders will be the same. Sometimes may not be the same. So that those things you can view here. The first order both are same. Even second order, third order, left side, right side. So when you move on to the fourth and fifth order, you can see the left side is 6.4 and right side is 6.2. And when you move to the fifth order, left side is 8.4 and right side is 8.0. In order to minimize the error only, you are taking this mean value. And then you have to calculate y is equal to root of x squared plus d squared. This column will guide you. So you know what is x from this previous column, and d, the distance between the grating and the scale, which is noted down as 23.5 centimeter. So square that, and x square, when you after squaring x, substitute here, after squaring d, substitute in this formula, and you will be arriving at 24.05. You are allowed to use the calculators. So by using calculator and do this calculation, which is 24.05, like that you will repeat for various orders, substituting x value and d value, square x value and square d value, add those two values and find the square root. So that is how you can complete this column. Coming to next column, sin theta is equal to x by y. So this previous column is y. What is y? Root of x squared plus d squared. So you got y value. And similarly, you know the mean value is x. So sin theta is x by y. So 1.6 by 24.05 will be arrive at 0.066. Like that you can complete for the rest of the orders. And then what is our aim is to calculate the wavelength of the laser beam. The formula for the wavelength of the laser beam is lambda is equal to sin theta by nm meter. So where lambda is wavelength of the laser beam, which is in meters, and theta is angle of diffraction, which is in degrees, and n is the number of lines drawn in the grating element. So for 2500 lines per inch, we have to convert to lines per meter. So 2500 lines per inch, when it is converted to lines per meter, you will be arriving at n is equal to 1.010 into 10 power 5 lines per meter. Hope you remember when I show the grating element, I have showed you 2500 LPI. So LPI is lines per inch. For our calculation purpose, we want to change this lines per inch into lines per meter. So when you do that, you will be arriving at 1.010 into 10 power 5 lines per meter. So this is your n value. M, in the formula you have m, which is order. You know, first order left side, first order right side, that we have done. No? So like 5 orders we have done. When we do for the first order, we will substitute m is 1. When we go for second order, m is 2. Like that up to 5. So this is about the formula to determine the wavelength of the laser beam. Lambda is equal to sin theta by nm meter. You know sin theta, you know n value, you know for which order we are going to calculate. So in that way, I have done one calculation for you. For the first order m is equal to 1. Lambda formula is lambda is equal to sin theta by nm. Unit you should write along with the formula meter. Then what is sin theta value? Substitute the data. Sin theta is 0.066. from the tabular column which we have calculated. We know sin theta is 0.066. So in this case you substitute sin theta is 0.066. N just now I showed you for 2500 lines per inch, when it is converted to lines per meter, N is 1.010 into 10 power 5 lines per meter. This N is common for all the orders. And lambda you have to find out. Substitute sin theta as 0.066 divided by N as 1.010 into 10 power 5. M is first order, so substitute 1. Suppose if you are doing it for the second order, you have to substitute M is 2, sin theta is 0.132. Okay, since I am showing here for the first order, M is 1. So when you do with calculator, 0.066 divided by 1.010 into 10 power 5 into 1 will be arrived at 653.4 into 10 power minus 9 meter, which is 653 nanometer. So this lambda value for the first order has to be tabulated in this column, 653.5. Commonly I have written 10 power minus 9. You need not repeat every time 10 power minus 9, 10 power minus 9. When I do here, it is meant for all the values under this column. And similarly, by doing the calculation for the second order, third order, fourth order and fifth order, you will be arriving at 653.4, 648.8, 626.2, 633.9, 639.6. So by taking the mean value of these column, that is what is called as wavelength of the given laser source. So the mean value has been found to be 643.88 into 10 power minus 9 meter or 643.88 nanometer. Anyway, you can give your answer either in meters or in nanometers. So that is how you have to do this wavelength of the given laser beam. The experimental part is very simple. Only you have to do much calculation. So all the calculation has to be shown, like sin theta calculation, lambda calculation for all the orders. This column calculation and this column calculation you have to show separately. I have done one sample calculation for you. These things you can, mean value you can do directly, and y is equal to root of x squared plus d squared, that also you can do directly. But for sin theta is x by y, and for lambda is equal to sin theta by nm. For all the orders you have to show separately, and then take the mean of this lambda column. Lambda is equal to sin theta by nm. You will be getting the wavelength of the given laser source, which is around 600 nanometer. So in our case we got it as 643.88 nanometer. In the previous class, I have demonstrated how to determine wavelength of the given laser source. The continuation of that experiment is determination of particle size. So how you are going to determine the particles size by using laser beam, that I am going to demonstrate now. So the apparatus required for this particle size determination experiment is plain glass plate in which lycopodium powder has been spread. If you look into this glass plate, you can see to my right side it is very plain, to my left side lycopodium powder has been spread. So this is a glass plate where lycopodium powder has been spread partially. So the reason for spreading lycopodium powder on this glass plate is, I told you the aim of the experiment is to determine the particle size. So whose particles size we are going to determine is lycopodium powder. Has very small granules in it. So in that granules, what is the particle size we are going to determine. So one apparatus what we required for this experiment is glass plate spread with lycopodium powder. Now you can clearly view the glass plate plain part as well as the portion where it has been coated with lycopodium powder. See, half is plain which I am holding, that portion is plain glass plate, and the next half it is being coated with lycopodium powder. Hope you all can see the powder is coated in this part and this part is plain. So this plain glass plate coated with lycopodium powder will be using to determine the particle size. And to view the diffracted image, we use this screen. And of course we need laser source to pass through this glass plate. By passing through the laser source to this glass plate only, we can determine the particle size. So glass plate with lycopodium powder, laser source and screen are the apparatus required for this experiment. So when the laser source is switched on, light from the laser source is passed on to the glass plate where lycopodium powder has been spread. Due to the granules present on the lycopodium powder, the light which is being passed through that powder is get diffracted and the diffracted image is captured on the screen. So when we adjust the distance between the glass plate and the screen to a certain distance, you can see the diffracted image. So now I'll repeat. So as such, you can see only the spot on the screen. So to get the diffracted image, either you have to move forward and see. While moving forward, it is clear that there is no diffracted image seen, only the spot you can see on the screen. But when I move backwards, you can see the concentric circles appeared. Slowly it has been appeared on the screen. Once you feel it has been very much clear, you can stop moving the screen. So at what distance the diffracted image is clearly viewed on the screen, you have to stop moving the screen. That distance you have to note down. At what distance the diffracted image is clearly seen or clearly appeared on the screen, you have to note down the distance between the glass plate and the screen. I already told you, you have a calibrated scale fixed on the wooden stand. So from that, the glass plate distance and the screen distance, if you note down, subtracting one value from that of the other, you will be noting down what is the distance between the glass plate and the screen. So that has to be noted down. The distance between the glass plate and the screen is noted, and which has been expressed as capital D in this experiment. And the captured image on the screen, you see the center spot is bright, surrounding which you have a circle, and followed by you have two other concentric circles. Leaving the center spot, you have the circle surrounding that central spot is said to be first order. Mark this edge directly on the screen using pencil and mark on the right edge, left as well as right edge of the first order. Surrounding this bright spot, the circle which has appeared is said to be the first order, and then you can see the second order followed by, you can see this third order. So we will stop with two orders. First order surrounding the bright spot, mark this left edge as well as right edge, and surrounding this first order you have another circle which is second order. Mark that left side edge and right side edge, and then measure the distance between the edges what you mark for the first order as well as for the second order. I'll repeat. The bright spot you can see, surrounding which you have one concentric circle. Mark the left side edge and right side edge using pencil. Then take the screen and conveniently use scale and measure the distance what you marked on the screen. So when you measure this distance, obviously you'll know that will give the diameter of this circle, the first circle. That means diameter of the first order. Similarly, marking the left edge and right edge for the second order and measure the distance using scale, you can get the diameter of the second order. So note down that in a tabular column. I showed you just now the experimental procedure for determining the particle size, and then I showed there how to calculate the diameter of the first order and how to calculate the diameter of the second order, and those readings are tabulated and displayed here. So for the particular distance, that is distance between the glass plate and the screen, which is noted to be 20.5, for that distance the first order diameter is noted to be 0.9. Similarly, for the same distance, second order diameter is noted to be 1.5. and what we required is radius. So noting down diameter itself in that small circle, it is difficult. What we required is radius. So from the diameter we can calculate radius. So directly calculating radius is very tedious. That is why we are calculating diameter of the ring, and from the diameter we are calculating what is the radius. Diameter by 2 you will be getting radius. For first order it is 0.45, and for the second order it is 0.75. Then y is equal to root of x squared plus d squared. The same formula you have seen in the determination of wavelength of laser also. So x is here radius of the first order, and d is distance between the glass plate and the screen. So which is 20.5. So 20.5 square it, and then radius is square, add and find the square root, which is to be calculated as 20.504. Use calculator and do, and then you will be getting this value. And then for the second order, the same way you have to do the calculation, which is appeared as 20.513, the y value. And sin theta x by y. X is radius of the first order, and y is corresponding y value. For the first order, what is the y value that you have to substitute? So sin theta is equal to x by y. In this case, 0.45 divided by 20.504 is 0.0219. Similarly, for the second order, radius is 0.75 and y value is 20.513. So sin theta is x by y. X is 0.75, y is 20.513. When you divide this by this, you will be getting 0.036. The same experiment can be repeated for another distance, which is found to be here 17.5. This distance is not constant actually. While demonstrating where you are getting a clear diffracted image, you can note down that distance. The same procedure has to be repeated for one more distance. So which is here I have done for 20.5 and 17.5. See, once again I will repeat, I have not fixed the distance. For what distance that image is appeared clear, that distance only it has been noted here. So one it has been appear at 20.5, the another one it is appear at 17.5. So for 17.5 distance, first order, what is the diameter, what is the radius, and finding y value. And for y, from the y value, once you know x value and y value, you can calculate sin theta. 0.35 divided by 17.503, which is 0.0198. And similarly for the second order 17.5 distance, which is radius found to be 1.3 and diameter found to be 1.3, and corresponding radius is 0.65, and y value is y. How to calculate y? I'll repeat, squaring the radius and the distance. Distance is 17.5, that square, and radius is 0.65, that square, and add and find the square root. You will be getting 17.512. And sin theta for that is x by y. 0.65 divided by 17.512 appear to be 0.0371. And now we have to find out particle size determination. So what the data we want, all these things have been tabulated. We need to substitute in the formula. So the particle size determination formula is found to be, is given here as T is equal to 1.22 lambda m by sin theta, which is expressed in terms of meters. So lambda is, we have done the previous experiment, wavelength. So from that experiment you have to substitute wavelength value, and m is order, and theta is angle of diffraction. M is order of diffraction, and theta is angle of diffraction, and lambda is wavelength of the laser source. We already found wavelength of the laser source. That is in our first part. Substituting lambda from that, m, which order we are doing? Only we have done two orders. Either we are doing it for first order or second order. First order means m will be 1, second order means m is 2. And sin theta from the tabular column will be substituting here. And then after substituting those data in this formula, that is T is equal to 1.22, lambda is 643.88 into 10 power minus 9 meter. Lambda is 643 into 10 power minus 9 meter. M is order. We are doing it for first order. M is 1. and sin theta is 0.0219. So in that way we arrived at 35.869 into 10 power minus 6 meter. That means 35 micrometer is the particle size for the order 1 and distance 20.5. And similarly, when we do it for same distance second order, it is found to be 43.042 into 10 power minus 6. And we have done for another distance also, no, 17.5. First order for the distance 17.5, it is found to be 39.47 into 10 power minus 6. And similarly for 17.5 distance, second order particle size found to be 42.306 into 10 power minus 6 meter. By finding the mean value of these four, we can conclude what is the particle size of the lycopodium powder by passing the laser source. So I'll show what is the mean value. It is around 40. So I'll do this with a calculator. 35.869, 43.042, 39.47 and 42.346. All the four values add and divide by 4. So once you do, you will be getting as 40.181 into 10 power minus 6 meter. Either you can express in meter or 40.181 micrometer. So that is how you can get the particle size using laser diffraction grating. So the results should be the particle size measured using laser diffraction grating is found to be 40.181 micrometer. Third part of the laser experiment is determination of numerical aperture and acceptance angle. The apparatus required for this experiment is optical fiber, light source and measurement jig. So light source, optical fiber and measurement jig. So this is measurement jig and this is optical fiber. Regarding optical fiber and its structure, we have discussed much in our theory part. So we have this portion in our theory part also. The same we are demonstrating in our laboratory. So this is optical fiber cable and this is light source and this is measurement jig. In the measurement jig, you can see the concentric circles are being drawn in this place, where each circle measurement is given in millimeter. If the first circle, if I consider, whose measurement is 5 millimeter in diameter. Second circle measurement is 10 millimeter in diameter. In the measurement jig itself, all this data has been given. Hope you can see clearly the measurement jig part alone here. So the circles have been given in this part, and then length has been displayed in this case, which is given in centimeter, and diameter of the circle is given in millimeter. So there are 1, 2, 3, 4, 5, 6 circles are there. Each circle, first circle if I consider, which is 5 millimeter in diameter. So you can see there itself it is given 5, 10, 15, 20, 25, 30. So first circle 5 millimeter, second 10 millimeter, third 15, like that it goes on. Length is given in centimeter. Between 1 and 2, you can see there are 4 lines. That means each division is 0.2, 1, 1.2, 1.4, 1.6, 1.8, 2. So therefore, like that you can measure up to 7 centimeter, 2, 2.2, 2.4, 2.6, 2.8, 3. So what I want to convey here is each line is 0.2 centimeter. So this is about your measurement jig. To determine the numerical aperture, the optical fiber is connected to the light source, and once the light source has been switched on, it has been passed through this optical fiber and it has been focused on to the measurement jig. So where you have a concentric circle, there the light intensity will be fall. So what you have to do is you have to adjust the distance of this measurement jig in such a way at what length the light intensity is fully falling onto the first circle. So it is very difficult to find out for the first circle, because first circle is in 5 millimeter in diameter. At what distance it has been moving means it is not easy to calculate at what distance it has been find. It is at what distance the full intensity is fully falling onto the first circle, it is not possible to calculate. Instead, we will move on to the second circle onwards. So what is the length, the intensity of the light fully falling onto the second circle? So you have to calculate the intensity of the light fully falling onto the second circle onwards. So by moving on this distance, we can find out at what distance the intensity is fully falling onto the second circle. So for first circle, see, I can't find out the distance. That is why we are moving on to the second circle onwards. So now the intensity is fully falling onto the second circle. Second circle diameter is 10 millimeter. So what is the distance, what is the length it has been shown is 1.4. Distance for the second circle where the intensity fully falling, the length is noted to be 1.4. That has to be tabulated in the tabular column. So for this first circle, diameter is 1 millimeter. When we convert millimeter to centimeter, it is 1.0. And distance between the fiber and the screen, at what length the intensity is fully falling onto the screen, which is noted to be 1.4 centimeter. Length is given in centimeter and diameter is given in millimeter. Both has to be converted to one parameter. That is, here it has been converted to centimeter. So length directly 1.4 centimeter and diameter of the second circle is 10 millimeter. When it is being converted to centimeter, which is 1.0 centimeter. Similarly, we have to find out for the at what length the intensity of the light fully falling onto the third circle. What will be the distance between the fiber and the screen? This is the screen. The circles where it has been drawn, no, that is screen actually. In the measurement jig, the circles where it has been drawn is said to be screen. Now I'll be moving on, moving the distance of the screen. Between the fiber and the screen we have to move. So the intensity is fully falling on to the third circle. So the length is found to be 1.8. So 1.8 has been noted here, distance between the fiber and the screen, and third circle is 15 millimeter. When it is converted to centimeter, it is 1.5. So like that we have to move for fourth circle. And why we need to struggle? Why not we go for sixth circle, seventh circle? Means, see, when I move, the intensity is fully spreading. We may not able to find out where it has been concentrating and which circle it has been concentrating. We may not able to find out exactly. It is fully spread out. For that reason, we are capturing only with the second circle, third circle and fourth circle. Second circle is very close to calculate the distance. It is somewhat fine, whereas the first circle, that is 5 millimeter in diameter, we can't find out the distance at where it has been found. We have to go inside and then find. That is why we are concentrating from the second circle, which is 10 millimeter in diameter, third circle 15 millimeter in diameter, and fourth circle. But when we move beyond, no, the intensity is not that much strength to spread into that particular fifth circle and sixth circle. That is why we are stopping with second, third and fourth circle. So the readings have been tabulated here. As for the second circle, length is 1.5 and diameter is 10 in terms of centimeter, which is 1.0. And similarly for the third circle, diameter is 15 millimeter, in terms of centimeter it is 1.5 and the length is 1.8, so on. And to calculate the numerical aperture, the formula is W divided by root of 4L square plus W square. And to obtain acceptance angle, theta is equal to sine inverse of numerical aperture. So what is this? L is distance between the screen from the fiber end. Distance of the screen from the fiber end, and W is diameter of the light spot. Light which has been spreading onto the particular circle. So W is diameter of the light spot and L is the distance of the screen from the fiber end. So by substituting those values in this formula, so here W is, that is diameter of the second circle, which is 1.0 centimeter, and whose length is 1.4 centimeter. Substituting in this formula, W place length, substitute 1 divided by 4 into L is 1.4, L square, and plus W is 1 and W square is 1 square. So by calculating this, you will be arrived at NA is 0.336. Sine inverse of NA is acceptance angle. So theta is equal to sine inverse of NA. In the place of NA, you have to substitute 0.336. So which is found to be theta is 19.63. Similarly, when the calculation has been done for the circle 2, that is for 15 millimeter in diameter, 1.5 centimeter, which is actually third circle, this is second circle, and this is fourth circle. And then when we proceed, we'll be I have arrived at 19.63 for the second circle, and for the third circle I have arrived at 22.58, and for the fourth circle, which is 22.58 acceptance angle. And numerical aperture is like this. So when we add and take the mean value of this numerical aperture, so which is found to be 0.368. So the numerical aperture of the given optical fiber is 0.368 in this case. And acceptance angle of the optical fiber is 21.59. The need for finding out the acceptance angle is whatever be the light is launching onto the optical fiber will not suffer a total internal reflection. Only the angle at which it has to be suffer total internal reflection we have to find out, which is found to be 21.59. The angle at or below which the total internal reflection takes place is said to be what is called as acceptance angle. So 21.59 is the acceptance angle in this optical fiber. So once again I will repeat, whatever be the light is launching onto the optical fiber will never suffer total internal reflection. We have to launch in one particular angle. For that, acceptance angle has to be found. So for that reason only, numerical aperture and acceptance angle determination has been done in this experiment. Students, hope you all clear about how to determine the wavelength of the laser. So I have demonstrated and showed you, and also how to do the calculation I have shown. So in that way we will be completing and doing the experiment in our laboratory to determine the wavelength of the given laser source. When you do in lab, it will be much more clear, and then repeatedly you keep watching this video, and then if at all any doubts, please feel free to post the queries. Thank you.